Good day, doctor. My name is Sri Karthikeyan, and we are from IDP Group 011.
And my name is Dinesh Nagarajan. And my name is Tivanisaro Nagarajan.
Everyone, today we are pleased to present our integrated design project entitled Flexible Textile Antenna Design for Wearable Communication Applications. In recent years, the rapid development of wireless communication and wearable technology has significantly changed the way healthcare and personal monitoring system operate. Wearable devices such as smartwatch, fitness tracks, and medical monitoring system rely heavily on wireless connectivity to transmit real-time data. For those systems to function effectively, however, most conventional antennas are designed on rigid substrates like FR4 or Rogers material. While these antennas perform well electrically, they are not suitable for wearable application because they are stiff, bulky, and uncomfortable when placed close to the human body. In addition, rigid antennas are more prone to performance degradation when subjected to bending, stretching, or body movement. Another major challenge in wearable antennas design is the interaction between the antenna and the human body. Human tissues are loosey and can absorb electromagnetic energy, which may cause detuning, reduced radiation efficiency, and potential safety concerns. Therefore, variable antenna must be carefully designed to ensure good performance while maintaining user comfort and safety. To address the challenges, textile-based antennas have emerged as a promising solution. Textile antennas are lightweight, flexible, low cost, and can be easily integrated into clothing. They are also allow the antenna to conform naturally to the human body, improving comfort and variability. Because of this advantage, textile antennas are increasingly studied for application in wireless body area, networks, health monitoring, and smart clothing. In this project, our focus is on designing a flexible textile antenna that operates efficiently in the 2.4 GHz industrial, scientific, and medical band, which is widely used for Wi-Fi communication. This frequency band is particularly important because many wearable and IoT-based health monitoring systems rely on Wi-Fi for data transmission. The main aim of our project is not only to design an antenna that operates at the desired frequency, but also to evaluate how different tactile material affect antenna performance. Tactile, textile material vary in terms of dielectric constant, thickness, moisture absorption, and fabric structure, all of which can significantly influence the resonant frequency and impedance matching of the antenna. Therefore, the specific object of this project to design a flexible and wearable textile antenna suitable for body-worn application. To achieve good impedance matching with return loss below negative 10 dB, ensuring efficient power transfer. To analyze antenna performance using simulation and practical measurement results, to investigate the impact of different textile materials, namely cotton, jeans, and polyester. And finally, to assess the antenna potentially for future wearable health monitoring and IoT-based application. Finally, to assess the antenna's potential for future wearable health monitoring and IoT-based applications. By achieving these objects, this project aims to demonstrate that textile antennas can serve as a reliable alternative to conventional rigid antennas, especially for wearable systems that requires flexibility, comfort, and efficient wireless communication. In the next part of this presentation, my teammate will explain the antenna design methodology, structure, and key performance results. Thank you.
Thank you, Sri Karthikeyan. I will now explain the antenna design methodology, structure, and performance analysis used in this project. The antenna was designed using a schematic simulation to fabrication approach which is CST Studio design. First, the operating frequency was selected based on practical variable communication requirements. The 2.4 GHz ISM band was chosen because it widely used for Bluetooth, Wi-Fi and IoT-based health monitoring system, making it highly relevant for wearable application. In terms of structure, the proposed antenna is textile-based circular patch antenna fabricated on flexible square substrate 100 mm by 100 mm. A circular radiation patch with radius of 33 mm is placed on the center of substrate. This circular geometry was selected because it provides stable radiation characteristics and is less sensitive into minor fabrication compared to regular designs. The antenna is excited using a microstrip feed line with a length of approximately 35 mm to achieve proper impedance matching in the standard 50 ohm source. And insert feed and slot structure were introduced. This design modification allow fine tuning of an antenna's input impedance without significantly increasing the antenna size, which is important for variable systems. During the design stage, several parameters such as patch dimension, feed position, and substrate properties were carefully optimized using electromagnetic simulation software. The goal of this optimization process was to minimize the return loss at the target frequency while maintaining a compact and flexible structure. From the simulation result, the antenna shows a strong resonance of 2.4669 GHz with a minimum return loss of negative 31.985 dB. This value is significantly lower than the common accepted negative 10 dB threshold, which indicates excellent impedance matching in practical terms. This means that very little power is reflected back to the source and most of the power is effectively radiated by the antenna. In the radian of return loss, the voltage standing wave ratio, which is called VSWR, was also evaluated at the resonant frequency. The VSWR value is approximate 1, which represents nearly ideal matching conditions. A VSWR close to 1 confirmed that the antenna was minimal mismatch losses and highly radiation efficiency. This result demonstrates the antenna design was electrical stable and well suited for variable application operating in the 2.4 GHz Wi-Fi band. The strong impedance matching also provides a solid foundation of integrating the antenna with future wireless module or health monitoring sensors. After completing the design, the simulation stage, the antenna was fabricated and tested using different textile materials. In the next section, my teammate will present the experimental material comparison result, discussion the application, and identify the most suitable textile substrate for the variable antenna project. Thank you. Okay, now we're going to test for antenna 1, which is cotton material. Okay, the frequency set between 1 to 5 gigahertz and the frequency drop at 3.623 gigahertz and negative 35 or 36 dB. That's all. Okay, now we are going to test for material of antenna 2, which is cotton jeans. And once we get it calculate, the frequency have go down to the drop to the 4 gigahertz and the dB will go for negative 10, almost for negative 10, and the range is between for 1 gigahertz to 5 gigahertz, and we got for 4 gigahertz.
We want to test the antenna on polyester material. So let's go. This is a frequency. Set the frequency to 1 gigahertz between 5 gigahertz and then connect the cable to antenna, and then it shows if it's negative, if it's above negative 10 the dB, it's good for receiving signal. Thank you.
Now, I will explain the practical material comparison, application, and final conclusion. In this project, we fabricated and tested the antenna using 3 textile substrates, which is cotton, jeans, and polyester. Each material exhibits different electrical behavior due to variation in dielectric constant, thickness, and fabric structure. For the cotton material, the antenna resonates at 4.05 GHz with a return loss of negative 17.66 dB. Although impedance matching is acceptable, the resonant frequency shifts significantly higher. This occurs because of cotton has a lower dielectric constant and looser fiber structure, reducing the effective electrical length. Therefore, cotton is more suitable for higher frequency wearable applications, but not ideal for Wi-Fi based health monitoring. Next, for the jeans material, the antenna resonates at 3.57 GHz with a return loss of negative 7.72 dB. Since this value does not meet the negative 10 dB requirement, it indicates poor impedance matching. The thickness and the non-uniform structure of the animal introduces losses and impedance mismatch, making jeans the least suitable material for the application. Next, for the polyester material, the antenna resonates at 2.207 GHz with a return loss of negative 16.38 dB. These results show a good impedance matching and a resonant frequency close to the 2.4 GHz band. Polyester informed synthetic structure improve electrical stability, making it the best textile substrate among the three. And in the term of application, this antenna can act as a communication hub for variable system, enabling wireless transmission of health data such as heart rate. Bro, stop பண்ணுங்க. Okay. Well, in the term of application, this antenna can act as a communication hub for variable system, such as enabling wireless transmission of health data such as heart rate and body temperature. Although IoT hardware was not integrated due to the time constraints, the antenna is fully compatible with Wi-Fi based health monitoring system, making it suitable for future expansion. The project successfully demonstrated high performance flexible textile antenna with excellent impedance matching at 2.4 GHz. Experimental results confirm that polyester is the most suitable substrate for variable application. Well, the project successfully demonstrated a high-performance flexible textile antenna with excellent impedance matching at 2.4 GHz. Experimental results confirm that polyester is the most suitable substrate for variable application. This work highlights the importance of material selection and shows strong potential for future variable and health monitoring system. That's all. Okay, next, for marketability and functional details. For the cost effectiveness, use Impex's radiator available textile such as felt, jeans, and polyester instead of costly rigid substrate like a 4R4 or Rogers. This make it highly variable for mass production. For the next, ease of fabrication. Implementation use standard textile cutting and conductive material application, fitting seamless into existing garment manufacturing process. And the third, commercial facilities. Multi-band operations such as 1.8 GHz, 2.4 GHz, and 3.5 GHz ensure compatibility with LTE, Wi-Fi, and 5G networks, eliminating the need for multiple antennas. Next, safety and compliance. Maintain SAR levels, example as 1.4 for polyester, while below the international safety limit of 2.0, essentially for commercial body-worn devices. And for the healthcare market, can be embedded in medical garments to monitor vitals like heart rate and oxygen saturation in real time with ultra low 5G latency. For the sport and fitness, enables real time tracking for athlete performance metrics such as speed, hydration, heart rate without threatening natural movement. Okay, for the defense and public safety, integration into tactical gear supports secure high-speed communication, GPS tracking, and live video feeds for the mission-critical operations. And the last but not least, industrial IoT, which is engaged workplace safety and supply chain tracking when embedded in industry in form of or protective gear. That's all.
For the comparison parameters on material cotton for resonant frequency is very high, and the material jeans is high, but for the polyester material closest to 2.4 GHz. Furthermore, S11 performance for the material cotton are good, but jeans are poor. By the way, the polyester is good. For the parameter dielectric stability, cotton is medium, jeans is low, and polyester are high. Fabric uniformity. For the material cotton, fabric uniformity is medium, and the jeans are poor, but polyester are very excellent. Wearable suitability. For the material cotton, the wearable suitability is medium, but for the jeans are low. Whatever, polyester is very high. So, for the health monitoring, polyester is very good more than cotton and jeans. Thank you.
Okay, for the cotton, we can use for Wi-Fi and IoT application. So this cotton material can use for the variable antenna.
Okay, for the material of a chains is not acceptable for the Wi-Fi compressions, which is only can transmit and receiving the signal only.
Furthermore, finally, for the material polyester are more greater than cotton and jeans. So this material polyester can use for Wi-Fi applications and can transmit signal easily. Thank you.